Well, welcome back. This is Calc 1 by Dr. Oz. This is the third video in a series of 4, and we are talking about Fundamental Theorem of Calculus. And in the first 2 videos, as a recap, we learned how to evaluate a definite integral using the Fundamental Theorem of Calculus. And then we talked about the mean value theorem for integrals, and finally we talked about the average value of a function over a closed interval. And now we're going to start the second fundamental theorem of calculus. Let's start. As a quick recap, the fundamental theorem of calculus is defined as you see here. So if you have a continuous function on the closed interval AB, and if you know an antiderivative of little f, let's say like it's called capital F, then the definite integral from a to b of f of x dx is defined as antiderivative of little f evaluated at b minus antiderivative of f evaluated at a. And in fact, we use the notation here that was f of x, bracket notation, lower limit and upper limit. So here we just realized that the upper limit is always a constant, which is in fact b, and the variable of integration is x. However, we might work on a slightly different situation where x could be used as the upper limit of integration. So to avoid the confusion of using like x in too many places, we want to make the variable of integration to be t, so that we will be allowed to use x in one of the in one of the bounds. So in fact, in this case, it's the upper bound. So to just sort of like make the distinction between a definite integral where the upper and lower limits are constants. So we're talking about having a number in the output. So the evaluation of the definite integral is going to spit out a number. And in fact, here f is a function of x, and x is the variable of integration. So now a slightly different version of this is where you have the upper limit to be x. And again, to avoid the confusion, we make the variable of integration to be t. So once you do this type of definite integral where the upper limit is x, the result is going to be a function of x, and we call that capital F of x. And in fact, the second fundamental theorem of calculus, is going to relate capital F, this capital F here, and to this little f here. To give you an idea about what is the meaning of x in one of the upper limits, I wanted to come up with this example, which is the integral from 0 to x of cosine t dt, and we know that the result is a function of x, and we call it capital F of x. So once we have capital F of x coming out of this definite integration, the question is asking you to evaluate capital F at 0, pi over 6, and all the way to pi over 2. So to be able to handle this problem, we use the first fundamental theorem of calculus that allows us to sort of like evaluate this integral. And all you need from the first fundamental theorem of calculus is just an antiderivative of cosine t, and we know that it's sine t in fact. And we use the bracket notation, lower limit 0 and upper limit x, and this is equal to sine evaluated at x minus sine evaluated at 0. And that's in fact, since sine 0 is equal to 0, that's equal to sine x. So once you do this definite integration, this capital F is no different from sine x. All right. So in the next step, well, obviously we're going to evaluate sine at 0, sine at pi over 6, sine at pi over 4, and so on. But what is the meaning of this geometrically? And one thing that we know from the earlier sections, that if you have a non-negative function to start with, and if you want to integrate that over, let's say, this domain 0 and x, the result is in fact the area between the curve and the x-axis, and obviously x's are stuck in between lower and upper limits. So for example, when I say like 0 to pi over 4 cosine t dt, it's the area between cosine and cosine t dt. So it's the area between the cosine function and the t-axis, where x's are in between 0 and pi over 4. So let's look at this problem from the geometry point of view and see what it corresponds to. All right, so we know that f of x equals sine x, capital F of x equals sine x, and well, f of 0 is sine 0, which is 0. Capital F of pi over 6 is sine pi over 6, it's 1/2. And all the way to pi over 2, and sine pi over 2 is equal to 1. But in terms of the area between cosine, the graph of the cosine function and the t-axis, where we play with the x values. So when x equals 0, as you see that there is no area to talk about because the lower limit is 0, upper limit is 0. So capital F of 0 for that reason is 0 because there's no area here. And when you change x to pi over 6, that means I'm talking about this much of area between the curve and the t-axis. And when x equals pi over 4, the area gets bigger, and eventually when x is pi over 2, the area becomes 1. Right, so what's really going on here? Well, you can think of the function capital F of x as accumulating the area under little f from t equals 0 to t equals x. And as I said, for x equals 0, there's no area to talk about, and for x equals pi over 2, the area is 1. So this interpretation of an integral as an accumulation function is used often in many real world applications. So in fact, take this f as accumulating the area, because every time you move in this direction, the area accumulates. All right. So now it's the best time to talk about the second fundamental theorem of calculus. So here's the statement of that. So if you have a continuous function on an open interval I containing the lower limit, then for every x in the interval, I can take the derivative of this definite integral where the upper limit is x, and I can get exactly the same integrand but written in terms of x. And in fact, we defined this definite integral as capital F of x earlier, and then this turns out to be equal to little f of x, which essentially means that f prime of x is little f. So we know that capital F is an antiderivative of little f by using this kind of like relationship. So the second fundamental theorem of calculus, in fact, relates capital F to little f. And in fact, when you take the derivative of the integration here, so doing and undoing, you get back to what you start with, but written in terms of x, not t, because t is the dummy variable and t is the variable of the integration. All right, let's finish this video with an example. So it's asking taking the derivative of the definite integral where the upper limit is x. Well, first thing to be able to use the fundamental theorem of calculus, the second one, is to check, first define a function, which is the integrand in fact. So f of t is radical t squared plus 1, and we want this function to be continuous. Here we go. Well, this function, for no matter what t you put inside the square root, is always positive, so it's in fact continuous on the real line. Okay, so that fulfills the requirement in the second fundamental theorem of calculus, and the derivative of the definite integral is in fact the same function f of x, so no t anymore, f of x equals radical x squared plus 1. All right. So this ends this video. Please watch the next video. I'm going to talk about the net changed theorem, and that's going to be the last video in this series. Thanks for watching. I'll see you in the other video.